Good morning, Hassler here. I'm going to do the lesson on 5.1. It starts out by saying if you've ever been in a car, when the driver slams on the brakes, you know that the car does not come to a stop immediately. Braking distance refers to the distance a vehicle will travel from the point when its brakes are fully applied to when it comes to a complete stop. So what are some factors that you think will affect the car's braking distance? Okay, well, some things that come to mind might be the condition of the brakes, right? If they're brand new brakes, I think you're going to stop faster. If they're old, worn out brakes, I think it's going to take a longer time for you to slow down. I might say something like the condition of the brakes. There we go. It might depend on the model of the brakes or the model of the vehicle, so type of car. Sorry about my pen. There we go. If it's a truck, which is going to be way heavier than a smaller vehicle, the heft of that could come into play when you're looking at the braking distance. I might also say something like the speed of the vehicle, right? It might depend on how fast you're going. So these are all things that could come into play when you're looking at braking distance. Again, braking distance is the distance you travel after you apply your brakes to the point where you stop. So the graph shows the relationship between a car's speed, how fast it's going, and its braking distance. Some values are also given in the table below. All right, so I just want to talk about this here real quick. So this is how fast the vehicle is traveling. So when the vehicle is traveling 0 miles per hour, the braking distance is 0. Well, that makes sense because if the vehicle is traveling 0 miles per hour, the vehicle's already stopped. So there's no braking distance. But if the vehicle is traveling 20 miles per hour, then there's a braking distance of 19 feet. So if I'm traveling 20 miles per hour, when I hit the brakes, I'm not going to come to a complete stop until 19 feet later. Okay, so it's kind of like this is our x, right? If I look at the x-axis on my graph, it's the speed, and this is the y. And you notice that that's going to be my y-axis, that braking distance. Okay, so let's take a look. It says, let's do this. What is the braking distance of a car driving 60 miles per hour? Okay, so I can look at the table. I've got 60 miles per hour here. And when I look at the table, 60 miles per hour, it looks like I'm going 170. 171. So what is the braking distance? It would be 171, and we'll put a label with that, feet. So what is the braking distance of a car driving 40 miles per hour? Okay, well, in this particular case, again, I could look at my table, but my table actually has a blank there for braking distance, that 40. So I'm going to come over to my graph, and I'm going to look for a speed of 40 miles per hour. And I'm going to follow that up till I hit my function, and then I'm going to follow that over. All right, so it looks like we go 50 to 100. Halfway between 50 and 100 is 75. So I'm going to estimate that it's going to be a 75-foot braking distance. And you know what? Let's actually put that in our table. Right, so we could actually use the table, or we could use the graph just to verify. If I look over at the 60 miles per hour and I travel up, that's going to get me, that seems reasonable to be about 171 for this problem here. But the table gives me the exact answer, which makes it a whole lot easier. I'm going to actually throw some new notation at us today. And so oftentimes we deal with multiple functions. This table and this graph happen to represent the same function, the same two functions. But often we talk about two different functions at the same time. And so we like to give names to those functions. And so if this is x speed, then we actually call this function, f for function, f of x. All right, and so we say f of x. That's how you would pronounce it. And what that means is that if I have a braking distance of 60 miles per hour, 60 is the x. And so instead of saying find y when x is 60, that's what this says. This says find y when x equals 60. That's a lot of words. And we have talked in math that mathematicians are efficient. So instead of saying find y when x is 60, or instead of saying what is the braking distance of a car driving 60 miles per hour, and we like to be more efficient. We like to say, hey, I want you to find f of 60. 60 is my input, that's my x value. I want to know the y value when the x value is 60. And that y value when the x value is 60 is 171. And so we write it this way. Similar idea here. What is the braking distance of a car driving 40 miles per hour? Well, really, that's saying find y when x equals 40. And again, we are mathematicians, and so we like to be brief. Instead of writing those words, we say, what is f of 40? Again, 40 is our x value. And so we say, what is f of 40? Well, f of 40 is 75. And so it turns out that we have this x. That's what I'm going to put into my function. And then this y. That's the answer that I get out. X, that's what I'm going to put into my function. Y, that's the answer that I'm going to get out. All right. Let's take a look at 3. It says the ordered pair 73, 254 is on the graph. What does this point tell you? Well, this is my x and this is my y. So it tells me that if I'm traveling at a speed, so a car traveling at a speed of 73 miles per hour, we'll have a braking distance of 254. And again, I just want to bring back in this function notation. This is a lot of words to say a car traveling at a speed of 73 miles per hour will have a braking distance of 254. And we should be able to interpret what these numbers mean. So I'm actually happy with these words. We need to know what the numbers represent in the context of the problem. Mathematically speaking, notation-wise, we can say f of 73 is equal to 254. And that would be the same or similar to writing this ordered pair. And so this is this new notation that we're going to be talking about over the rest of the semester. All right, a car took 200 feet to come to a full stop. Estimate the speed at which the car was traveling before the brakes were applied. All right, well, I could take a look at my table, and if I take a look at my table, a braking distance of 200 falls somewhere between 171 and 305. And so that means that my speed is somewhere between 60 and 80. Not super helpful. So I'm actually going to go to my graph, and I'm going to look at where 200 is. That stopping distance of 200 is on my graph, and I'm going to follow that over to my curve. And there we are. So I'm going to drop down. So it looks like we've got 60, maybe, let's see, what are we going by here? 20, so 5, 10, 15, 20, 25, 30, 35, 40, so 60. So 65 would be my answer here. Oops. And so we would say 65 would be the speed. Okay. And again, just to think about this notation, we're saying, hey, find this value so that the answer is 200. And the value that would give me an answer of 200 would be 65. So that's what we're trying to find. All right, so then after that, we gave ourselves a chance to talk about the interpretation of what f of 20 is and using function notation to rewrite the sentence in number 6. So f of 20 means that if your car is traveling 20 miles per hour, let's see, then I have to go figure out what that stopping distance is. All right, so I actually can go to the table to do that. My table has 20, 19. And so if I'm traveling 25 miles per hour, then I'm going to have a braking distance of 19 feet. In other words, f of 20 equals 19. And use function notation to express that a car is traveling 45 miles per hour. So f of 45, 45 is my x value or my input. And the output, that braking distance, is 96. And so this is what we talked about in class. And then we took some notes. So I have a second video on the notes page, filling out notes for section 5.1. And then after that, we had some time to kind of figure out the check your understanding for 5.1, see if you know what's happening. So the key will be posted for you for the check your understanding, but it's a chance for you to see if you understand this function notation and how to interpret it. If you have any questions, as always, let me know.